So this time I'm very happy to introduce our colloquium speaker, Xiang Lorraine Li. So Lorraine was previously a young investigator at, first what she is now. Lorraine is a new assistant professor at UPenn CIS and just moved here at the same time as all the first year PhD students. So also first year Pittsburgh resident. And previous to that, she was a young investigator at AI2, and then before that got her PhD at UMass. She's doing a lot of very interesting work on Commonsense, specifically probabilistic Commonsense, which she's going to talk about today, through both the focus of machine learning and also evaluation and thinking about what sorts of common sense we should be modeling in the first place. For every colloquium presentation, I'd like to talk about a connection that I have with the speaker, and my connection with Lorraine is that I introduced her spotlight presentation at iClear in 2019, ages before COVID, and so I've known about her work for a long time and was very excited about it then, and am excited to hear about the new stuff now. So please take it away.
Thank you. Thank you. Yeah, thank you for the nice introduction. And I'm excited to talk about my work here today about probabilistic common sense in language. Feel free to interrupt me at any point if you have any questions. And let's get started. So as we all know, there has been impressive progress in the past decades. And then these AI technologies are increasing their deployment and impact in our daily life. So interactions. Oh yeah, let me use this one, because this is not for this room mic. Is this better?
I don't think it's on.
I think there might be.
Oh.
Try now.
Cool. Is this better now?
Yeah.
Oh, great. Yeah, so this is just AI techniques are increasing in their deployment and impact. So the interactions with these systems becomes increasingly more important. So take this Google Home example. Someone asks, like, they're not able to find their phone, they ask for help. Hey, Google, can you call me, please? Google said, you sure? And then this person said, yes. Google say, okay, I will call you, please, from now on. So Google made this mistake because Google doesn't know that please is not usually a person's name. And we, as human, all this is the key piece of missing information that is not get spoken in this dialogue. So we as human is able to communicate because we use common sense to fill in this missing blank. And that's why machine needs common sense too. And then you might ask, doesn't GPT-N model already have common sense? So I asked this question. Which one is heavier, a croissant or strawberries in the same size as a croissant? This is the GPT-3 response. A croissant is heavier. Let's look at ChatGPT. ChatGPT basically said the same thing, but with a lot more decent explanations trying to explain the wrong answer. And then now let's try GPT-4. It's so much more better. And the same as before, GPT-4 still said the croissant is typically heavier than the equal amount of strawberries. After trying all this examples, my answer to this is just not really. They don't really have common sense. Then let's go back to the fundamental question. What is common sense? So take this one example. They boil the water. We as humans shared massive background knowledge about this sentence, and specifically water. Like water is liquid, water needs to be held in a container. This is the background information that is beyond, knowledge that is beyond the information the sentence is conveyed. And the same applies for the action boil or boil water, like heat is needed to boil water and burner can provide heat. So this is common sense, which is implicit background information that is shared among all human beings about everyday matters. But it's extremely challenging for an AI system to possess such knowledge. The amount of background knowledge we shared for this single statement is massive. And the knowledge expands drastically when the number of sentences increase. Not to mention the millions of texts and documents we interacted with the system every day. It's almost impossible to store all this information in one single database. Furthermore, this useful background information in the sentence like, where is the water? What tool is used to boil the water? Is unstated. And there are usually multiple correct answers to this question, like water could be in a kettle, in a pot, in a glass, or even in a beaker. In addition, as you may already noticed, the likelihood of these answers are different. Intuitively, we would think water is more likely to be in a kettle than a beaker. So common sense is probabilistic. It provides us with a probabilistic assumption instead of a definite judgment. And this probabilistic nature makes it even harder for us to represent due to its uncertainty. And moreover, if we change this statement, they boiled the water and added spaghetti, the distribution of the answer changes as the sentence changes. And if spaghetti is replaced with a chemical item, now you could say beaker is the most likely answer. So this background knowledge we apply change as the basic statement changes. Common sense is also contextual and extremely flexible, which makes it even harder to model. And furthermore, you may notice it's not only applicable in the general domain, it's also very important in scientific domains, where common sense then becomes domain-specific knowledge shared among domain experts. And the domain knowledge exists in different applications in these high-impact domains, such as when we're generating new material synthesizing procedure in material science, understanding protein disease interactions in biomedical, or even making judicial decisions in judicial systems. So more specifically in judicial systems, it's important to notice that apart from this domain-specific common sense knowledge, there's also human bias. And this bias could come from real-life data. And this real-life data distribution not only contribute to common sense, but also human bias. And they're essentially just the bad kind of common sense. And both common sense and bias can be viewed as filling the implicit assumption. So we must be even more careful when we're ensuring that building models to make sure the model is making fair predictions in these cases. So yeah, that's enough of a motivation. My research focused on designing models and evaluations for massive common sense background knowledge. And I will go into the outline of today's talk. First, I'll start by talking about a probabilistic model we built for common sense, its training details and different applications. And followed by a systematic study and also the limitation of the fundamental building blocks of these large language models, transformers, on the compositionality on the highly compositional tasks, where it's highly related to common sense. And then finally, we'll talk about the evaluation of common sense to evaluate it in a probabilistic way and focused more on the long tail aspect of the distribution. So let's get started. As we mentioned before, we need a representation for common sense which can model such knowledge using probabilistic abstractions and principles. And in NLP, we typically learn vector representation. However, these vectors cannot naturally capable of encoding a full probability joint distribution. They usually rely on this post hoc vector dot product score to encode a specific form of conditional probability. And furthermore, if we look closer to these two data points, rabbit and mammal, mammal is a much more general concept than rabbit. But the vector representation cannot capture this generality of this word. And moreover, rabbit is a mammal, but mammal is not a rabbit. So the naive score function between vectors like dot product or cosine similarity cannot capture this asymmetric relationships between words. And this is where we develop this representation, probabilistic box embeddings, where it's actually naturally a region-based representation and could represent the generality of a concept. and can represent asymmetric relationships by just putting one box inside of another. And we could also represent probabilities using the volume of the boxes. So it naturally becomes a probabilistic model. More precisely, box embeddings are axis-aligned hyperrectangulars. This is a description of a two-dimensional box embeddings, but in reality, we train box embeddings up to 300 dimensions. And then in order to calculate the volume, which also represents the probability, it's just the multiplication of all its edge lengths. And because edge lengths cannot be negative, so here we just apply a value function. And then finally, the probabilities. A single box represents the unary probability of the concept, and the intersection of boxes represent the joint probability of two concepts. Naturally, you'll get a conditional probability representation by taking the division between the joint and the unaries. So this can be viewed as giving us a set of Venn diagram interpretation of this concept that the box embeddings try to represent. And in training time, to learn such representation, we usually use supervised training, where the training goal is to match this ground truth probability, and the loss can be anything. Here we used cross entropy, is the one we used most frequently. So before I dive into the training details, are there questions? Go ahead.
Why radio why use a radio to make sure that the size is not negative?
Mm-hmm. Oh, it's more intuitive if you think about it. If you have a negative edge length and you take the absolute value, what does it mean minus 10, and then it becomes 10? We just simply constrain, you can never go to the negative part, which will cause problems, and I will describe right now. Go ahead.
So is there any significance to having negative edge lengths, or is it just treated as zero?
Sorry?
Is there any significance practically to having a negative edge length in the box?
We never tried it. So practically, I don't know, but I think it will create problems when you try to calculate the intersection of two boxes. Right, yeah. Good questions. So let's dive into the training details and see why this value function is causing us problems. At training time, we'll randomly initialize all these box embeddings at random positions with random size. And they will have this ground truth probability they try to match, the unary, joint, or conditional probabilities. And for this specific task here we're going to dive into is this. We use a conditional probability to enforce the hierarchical relationship between concepts. And we wanted to essentially make sure that the trained embeddings follow this hierarchical structure, like a deer is a herbivore and also a mammal. The boxes will try to match to the target probability by moving towards each other through gradient descent. But there will be training difficulties. As we can see here, the deer and mammal boxes, they're initialized to be disjoint with each other. And as training goes, you can see how the probability is changing, the loss is changing, and the gradient changing as we move the deer box manually into the mammal box. It will not, in the first part of this training, the probability is not changing, loss is not changing, and gradient remains zero. Only if these two boxes start to touching each other, there are some changes in these values. So you may already know this. The zero gradient is a problem. And we first noticed this problem and solved it in a follow-up paper, Smooth Box. It's the iClear presentation Graham mentioned in the first time when he introduced us. So yeah, this is where here we simply replace this value function to a soft plus. And we also theoretically prove that this replacement is an approximation of applying a Gaussian convolution kernel on the edges. So here we're essentially smoothing this box edges. But there's more we can do, and there's more difficulties in this training paradigm. For example, here, the current boxes is one is inside of another, and the goal is trying to separate them apart. However, no matter how you move this blue box inside of this orange one, the gradient never changes. Same problem as before if we only have the conditional training objective, which is always 1. And what's even more concerning is it's in this crossing situation. No matter how you move these boxes horizontally or hierarchically, horizontally or like vertically, it won't change. The intersection remains the same. So later in Europe's last year, 2020, not last year, we tried to smooth the box corners instead of smooth the box edges. And as you can see clearly, this is the training loss or the conditional probability changes between all these 3 different methods. In hard box, you see there's a very hard boundary between all of this. In smooth box, the edges are smooth. Where in gamma box, everything becomes smoother. And then, yes, in this improved training where with gamma box, the boxes is able to escape from all those situations. So those are the training part of the box embeddings. Any questions? I will dive into application. Go ahead. Sorry? Oh, yeah, I will dive into the applications and talk about it more. Most of the times it comes with the data set itself, or we can compute it manually using the data set. Go ahead.
Is that the case too with the dimensions with the embeddings? Like, are the dimensions sort of in the data already, or do those have to be sort of discovered automatically?
No, the box embedding dimensions is a fine-tuned parameter. It's just like how many.
I meant like the orientation of the dimensions. So like, because it seems like boxes, they're not invariant to like rotations that don't match up along an axis. And so it seems like it'd be relevant, like basically the semantics of the different axes, or the different dimensions in the...
You mean the semantic of different dimensions in box embeddings? Yeah. Is there any semantic meanings of the... Yeah, that's a very interesting question. I remember we dived into it for the WordNet data, which I will talk about later. There isn't very obvious meanings with each dimension, but it might because the data was sort of noisy, and I would be interested to go back to check on this toy data if the dimension has any meanings. Go ahead.
Yeah, I'm just curious why boxes, why is she using Gaussian so around more smooth, it's even smoother, and have a lot of computational advantages?
Yeah, great question. The reason is because the intersection between two Gaussian, like actually one of the co-authors in this box embedding proposed the Gaussian embedding before this. And there was some difficulty of training Gaussian embeddings, and the intersection of 2 Gaussian embeddings is not guaranteed to be a Gaussian, right?
But how boxes is better in that case?
What?
Why boxes are better in that case?
Because the intersections of 2 boxes remains a box, right? If they're like axis aligned. Yeah, good question. Go ahead.
Gradients will change the size of the boxes. The box size becomes like then it becomes
Yeah, it's a very good question. We actually face that problem when we're training boxes. And the practical, we tried a very engineered solution to just clip the size or add some kind of regularization to force the box size cannot be too small. Yeah, great question. Okay, I will now talk about the applications of boxes. Where do we use this box embeddings in all these different scenarios? The first task is we created this toy data. It's a small hand-constructed ontology over 19 concepts. And along with this toy data, we designed the unary probability, joint probability, and conditional probabilities. So this kind of ground truth, it comes with the data itself. And then this is a trained two-dimensional boxes, which is a little bit hard to read, but let's look at the conditional probabilities. The middle one is the ground truth conditional probability that we trained the model on. And the left one is order embedding. It's one of the baselines we used in our work. And it's not doing a great job recovering it. And the right one is box embedding. As we can see, it's doing a much better job recovering the ground truth conditional probability. So one interesting thing from this small hand-constructed ontology is we could ask very flexible queries to this model. For example, now you ask, what's the probability of deer? It gives you this probability. And then what's the probability of animal? What's the probability of deer given its animal? And given its animal but not white. More complicated, given its animal and herbivore but not white and not rabbit. So, and furthermore, we can ask if it's an animal but not a herbivore and not white and not rabbit, the probability goes back to 0. So this is something unique with box embeddings compared to the vector embeddings because the vectors are trained in one type of conditional probability, where here is actually we're trying to learn a joint distribution over all the concepts. And then furthermore, that's just a toy data set. Furthermore, we tried it on this WordNet hierarchy, where the trees are much more larger, has 800,000 edges, and comes with conditional probability, which is just labels of 1. The conditional probability are all 1s. And this is application of boxes on this word level. And furthermore, we tried it on sentence level. So this each of these concepts is each of these short phrases is a box embedding. And back at the time, we just used the LSTM to encode this phrases and then convert them into box embeddings. Here we have the unary, joint, and conditional probabilities. So I will not talk about the detailed results because, as you all know, it's always going to be better than baselines. But I will talk about some more of the exciting recent works because we hear and the quantitative results on this. Oh, go ahead.
Can you explain how you generate a box embedding with an LSTM or a neural model?
Yeah, sure. Here we just take a LSTM to encode this sentence, and then after that we have two feed-forward networks, one to output the minimum coordinate and the maximum coordinate.
So I noticed that you're not really generating hierarchy. Typically, hierarchy does not have just more than one character, but when you actually allow this kind of structure. So what is the advantage or disadvantage to allow this kind of structure?
To allow the structure or to learn the structure. This is
To the design choice. So basically, what you're producing is not a tree, right? But you basically allow the, it's actually graph. But I'm just saying, what's the advantage or disadvantage by choosing this kind of structure? Tree structure.
It's not about choosing the structure. Boxes can represent any DAG, and I think DAG is just more commonly present in daily life than trees. A lot of our data are more DAG-like than a tree-like structure. Does that answer your question? Because it's not.
That's my question, but it's not aligned with
But it's not. I guess I'm trying to say it's not a design choice. Rather, it's a model that could learn any type of graphs, not any type of graph in the specific.
It is a design choice, but I think my answer to my question is the advantage is this kind of structure is better aligned with impressive than tree structure. So that's my answer. But I think it's very interesting.
I feel like logical structures could present in a tree structure as well, right? You can also say not one of the child, but the other.
Not all constrained because you have different like the blue box. Okay. But anyway.
But that's an interesting point. We can discuss more offline. Yes. Yeah, I wanted to say this more recent work about word2box. If you're familiar with word2vec, where basically learn a vector embedding unsupervisedly by reading a lot of corpus. And the training objective of a word2vec is two words that is within a certain window size in the context should be similar to each other. So here we replace all the vectors, two boxes. And we're just saying the intersection between two boxes within certain window size should be bigger than some negative examples. And here we just showed some really interesting example where we show what's the sum of the words that is property but not finance but is algebra. So we choose a few examples here, outputted by word2box, and a few examples here by word2vec. And we can see the box embeddings are capture more of this semantic meaning of the query we're asking than the basic baseline word2vec. And this is one more example, some properties that is not finance, but it's chemistry. So yeah, I think now this is the most recent work of word2box, and there's also a lot more works trying to use box embeddings to capture the joint hierarchy, Commonsense knowledge graph, entity typing, and yeah, just more recent word2box work.
Can you go back to how do you compute the set operations for word2vec?
That's a great question, and we just did addition minus with the typical vector operations.
A exclude B.
Like A minus B, and yeah, which might not be a good way to capture this, but there is no good way to, like, not that we can think of. There are probably some good ways, but we could not think of anything that is more applicable for vector embeddings. Yeah. So I'm going to wrap up on this box embedding section and move on to the next section. So if you have questions about this, feel free to ask now. Otherwise, I'll move on. Go ahead.
Thank you for joining us today. So far, it seems we've been seeing work on learning the embedding and also building a knowledge graph from it. Do you have maybe you've done work on it, but is there any examples for using these box embeddings, incorporating that into like typical models for performing various tasks?
I guess this entity typing one is an application of how we represent what the entity typing is, predict the type of an entity within a sentence. And here we're just representing the types using box embeddings and show that with this sort of representation, the model performs better than vector representations. This is some sort of a downstream task.
So, you know, everybody is thinking about large language models nowadays, of course. I see an obvious application where you take the output of a large language model and predict box embeddings, but I wonder if you were thinking about incorporating them into input also. So you said you had an LSTM where you could predict embeddings, but presumably that was just taking in regular word embeddings.
Yeah, yes.
I wonder, you know, normally, or very often we tie embeddings for the output and input, and I wonder if you ever thought about it.
Yeah, we actually was trying to work from that direction, but one thing that is in order to fully utilize the relationships between box embeddings in the input level, we sort of want to use the box embedding in the networks directly. And how do you constrain the networks to such that the basic operations in the network becomes basic operations between boxes? That's a hard question. Yeah.
Yeah, so my question is the box embedding that's enough or expressed enough for all the hierarchy structures? Because it is still in the Euclidean space, but for like structures, it could still be in a non-Euclidean space. So I'm just wondering what it can express or like.
Yeah, boxes can express all the DAG structures. In another paper that we proved it with its capability. And with comparisons, I'm not showing it here, but one of the slides I hided, we actually compare the model performance to Poincare hyperbolic space. So we compare the embeddings representations with Poincare and hyperbolic entanglement cones. Those are great questions. Thank you. And I'll move on to the next section. So yeah, as Graham mentioned, box embeddings is cool, but it's very simple. And now everyone is thinking about large language models. So let's turn our heads to large language models to say, how about large language models? What are the kind of limitations of large language models, specifically in modeling common sense problems? And that's the second part of my talk, limitations of current language models on common sense reasoning. And the first work I'm going to talk about is the limitation of transformers, which is the foundational building block of large language models on highly compositional tasks. And this paper just got accepted to NeurIPS. So here we wanted to ask the question, language models are impressive, but how about compositional tasks? One typical compositional task is multiplication. It's very simple for us, but how does language model do this? My co-author, this is one of the first authors. She asks GPT-4, can you multiply this 3-digit by 3-digit number? The result is wrong, because it should be this number, not this number. You could be saying, okay, but chain of thought has been improving result of all these models. Can you try to think step by step? To multiply this step by step, GPT-4 gives us a really reasonable, seemingly very reasonable solution, but the result is still wrong. So this is one of the examples, motivating examples. And in this paper, we aim to better understand what's possible or not possible with transformers, with this highly compositional tasks that requires multi-step reasoning. And the first task we've considered is multiplication, as I said before. How do we human compute this 49 times 7? The way we compute it is we take these two numbers, we do multiply by 1-digit operations, and then we carry one sum of the digit to the next step, and then we do sum, like all of this multi-steps. And finally, we reach to answer. So this is highly compositional and requires a lot of steps to reach to the final results. And the next task we're considering is a non-adjacent maximum sum subsequence. It's a dynamic programming task, where this task requires you to recursively break down this complex problem into simpler subproblems. The task here is just giving a list of numbers, and you're supposed to give me the maximum sum such that the elements in the sum are not adjacent to each other. So 4 for 1 is the maximum sum here. And we also go beyond this number tasks. We have a very, the task is most related to language with natural language task descriptions and reasoning steps. So here, this final task is S-tense puzzle. And the task here is you're giving n number of houses, and each house has m number of attributes. Like name, sports, and car. We also have some potential candidates for these answers. And your goal is trying to fill out this table with this clues that is given here. As a human, the way we solve it is just, let's take the easiest first. Arnold is in the third house. So we can fill in that cell right there. And the next step becomes a little bit more complicated. You need to think about take these two clues. The person who loves basketball is Eric, and the person who loves tennis and the person who loves soccer is next to each other. You take the combination of these two clues, and you're able to fill in 3 cells within this, in this final table. So we do this sequentially, and gradually you take all the clues and fill in all the tables. So this is just another very highly compositional task that requires you to think step by step, to take the clues step by step and apply them step by step. How do we tackle this problem here? Here in this paper, we define a computational graph. And this is just an example of computational graph for the multiplication task. And we use this computational graph to better understand how transformers are doing this task. But before getting to the computation graph details, how does the model work on this, just doing zero-shot prompting for all of these tasks? So here you see a heat map of performance on all of the 3 different tasks. And the x-axis is the problem size. It's like this is 5-digit by 5-digit for multiplication. And that's 6 houses for 6 properties for the puzzle problem. And that's the length of the dynamic programming problem. As we can see here is the transformer's accuracy decreases to nearly 0 as the task complexity increases. So here the task complexity is just defined by problem size, which might not be accurate. Some of the problem might be 6-digit by 6-digit is not going to be that hard. So we later define this with respect to graph complexity. When we break down our problems into computational graphs, how does the graph complexity related to the problem performance? And this is just another graph showing that as the graph parallelism is a metric we defined in the paper to measure the graph complexity. And as we can see, it's just as the graph gets more complex, your way as the steps getting more complicated in order to reach to the final answer, the performance gets worse. And then this trend remains the same with few-shot prompting and scratchpad prompting, where it's just think step by step. How do you solve this multiplication problem? The trend remains the same. Feel free to check the paper for details. So now it feels kind of rushed to just does it mean the model can't really solve these tasks? Maybe it's just because the model haven't seen enough task-specific data. So here we fine-tune the model. We fine-tune a really large model GPT-3 with a large amount of training data within reasonable budget. And one thing here, as we can see, similar as before, the x-axis is either the graph width or the problem size. And the gray part is the in-domain data performance, where we take 80% of the in-domain data. For example, multiplication, we train it all the way up to 4 by 2, and we take 80% of the 4 by 2 data as training, and then 20% as the evaluation. The in-domain performance with the blue line are all pretty good. But the moment you go out of the in-domain, you go to out of domain, the performance drops to nearly 0 with all of these tasks. So this means the systematic problem-solving capabilities do not emerge through this exhaustive training on task-specific data. But now you may say, well, as a human, if you just gave me 1,000, 10,000 of multiplication pairs with only input and output without telling me how to do it, I will be having a hard time figuring it out as well. Can we fine-tune the model with step-by-step instructions like this here?
Yeah, I don't understand why the blue curve have a sharp drop. The other two are more gradually declining. What is the phenomenon?
The blue curve is fine-tuned performance,
Yeah.
where the other two is 5-shot.
Sharp drop. Yeah.
Yeah, because the gray one, the sharp drop happens at in-domain data. When the evaluation data is at a similar problem size as our training data is, the performance is pretty good. Yeah.
Yeah. Okay.
Okay, let's move on. Yeah, then how about we train it with this step-by-step scratchpad, where we actually teach the model how to solve this problem. Surprisingly or not surprisingly, we see a similar trend. The moment the model goes to out of domain, the performance drops significantly. So that means even when training directly with the guidance on these computation steps, the model still fails to learn the component operations in a generalizable manner where you can apply it to out of domain evaluation. So this is just some empirical evidence, but what we actually wanted to know is why sometimes the model can make predictions correct with a 5-digit by 5-digit number. Why those happens? So we ask this question: what's the correlation between a model's generating a correcting output and having seen relevant subgraphs during training? So here, for example, this is our evaluation data, and this is the computational graph of the evaluation data. The blue part is the subgraphs that the model already seen during training. Then the model could just reduce the problem into a much simpler computational graph. Meaning if you already seen a relevant subgraph during training, the inference is only seemingly a highly compositional problem. And we show empirical evidence on this hypothesis, where here we show the blue line is the correct final answers. The red line is incorrect final answers. The proportion of the subgraph has been seen during training is much higher for the correct final predictions than the incorrect predictions. There are questions? This is one of my favorite part of this paper. Okay. So next I'll move to this. Also, I should advertise it. Noha, the first author, is going to give a colloquium at Pitt on October 13th. You're all very welcome to join her presentation to have a more comprehensive study of this paper. Go ahead.
How do you know the transformer has the capability to recognize or memorize the subgraphs that you see?
Oh, this is just an empirical counting, right? We count how many times it's seeing the subgraph in the training data.
Okay, thank you.
Yeah, yeah.
When you say the model has seen the subgraph, you actually mean the model has seen the direct answer of the subgraph instead of the subgraph itself?
It's a combination of both. I think we did the subgraph comparison where it has both of the computation steps and the final answer.
This is any subgraph.
Any subgraph.
And is this relationship stronger for subgraphs in different parts?
No, we didn't do that analysis, but that's an interesting question. Okay, cool. So now I'll move on to the next part. You've been talking about compositionality, then how about common sense? These models have also been shown to be very effective, impressive performance on a lot of common sense question answering tasks. And this is just like the fine-tuned state of art that is built on top based on this model, like BERT or Roberta at the time. So this fine-tuned performance could either come from this large language model itself or it could come from the common sense task-specific supervision, as we shown in the previous paper. When we fine-tune the model performs much more better. But here I wanted to stress that in this paper, we are now trying to study whether the model can solve this task or not. It's more like, does the model have common sense already? So the evaluation that we focus on this paper is a zero-shot evaluation in large language models. And at the time, the GPT-3 zero-shot was really impressive and even outperformed some of the state-of-art SOTA results at the time. So this begs the question of, do language models learn common sense? To answer this question, we performed a systematic study focused on the language model itself without task-specific supervision and without model parameter update. So in other words, zero-shot evaluation on language models. So here we focus on this 4 data set that is all multiple choice selection problems covering different type of reasoning types. And in order to do a zero-shot, we just concatenate the questions and answers together and then pass it into a language model, getting a score for each of this question, takes the maximum score as the prediction. And the score function here we used is a token level log probability. A language model here we evaluated is a Gopher. It's Gopher from DeepMind, where it has 280 billion parameters and is showing very impressive performance on all sort of different common sense tasks. Let's see the zero-shot performance. This light blue one is a random baseline, and the dark blue one is a zero-shot performance. Very impressive, especially for these 2 data sets. And it's even have a closer, smaller gap to fine-tune SOTA compared to random performance. However, for both of these 2 data sets, the model is struggling a bit more, social IQA and Venn Grande. So the next key question we wanted to ask is, how much of the model performance comes only from the answers? If we only give the answer to the model, how likely the model can give us the correct prediction? If the model really has common sense reasoning ability, the probability of predicting any answer, this answers should be independent of each other, and then the probability should be equal. So the performance should be similar to random baseline. But yeah, it's not as that. As with the answer only baseline, especially for HelloSwag and Pickup, we saw a much bigger jump with this language model, with this performance. So this probably means some of these options just inherently have a larger probability under this language model. And when we are creating data sets for evaluating common sense, we need to take consideration of this, to remove this data set bias. And then, but if we just train a larger and larger model, will it solve the problem? This is the graph with the performance graph range for all of these data sets, with the performance from 44 million model to 280 million parameters. So yes, as model size increase, accuracy increase. But the performance plateaus at a certain point where all of the 3 models are having a similar performance. Blindly training these larger models will not teach common sense, will not teach language model common sense. And those are just the 2, we did more analysis in the paper, but those are the 2 most important takeaways from the paper, I think. Where we learn from this paper is there are action items we should always compare to a stronger baseline when we report zero-shot performance with language models. And also we should evaluate common sense beyond the multiple choice selection problems, where this brings me to my final section of the talk, evaluation of common sense. There are questions?
So what is the connection between the first part and the second part of this second project? Because in the first part, you were trying to compose small sub-problems or solutions in order to get the final solution, right? But I didn't see any flavor in the second part. Like, did you try to like compose only small common sense concepts in order to get the final answer?
I'm glad that you asked it, because this first paper I just put it very recently. So it might feel like a bit disconnected, but I think there is an inherent connection between compositionality and how we think about how we as humans understand common sense. As I said in the contextual part, where common sense is contextualized. If you have different conditions, or if you have different components in your input and in your final reasoning, you need to combine the resource. You need to combine all the different aspects of the input to reach the final answer. And that combination could be just a distributional combination, like these are all there and I'm just trying to make the prediction. Or it could be a sequential manner, which is what we studied in the compositionality paper. And that requires more reasoning. That do you understand the rules? Can you apply the rules to a new domain?
I see.
Where I will.
Yeah, but it also depends on the complexity of the problem, right?
Yeah.
Because in the first part, you were trying to ask the model to extrapolate to a harder problem or a longer problem. But like for humans, maybe like as long as we see enough training data, we probably don't have to learn this, extrapolation capability, because only real-world problems can be solved using a finite number of steps. And this finite number of steps, the number or the complexity was already seen in the training data. So I feel like the first part and the second part are trying to tackle different types of problem, because
I feel like even as human, we are doing extrapolation. Like we never taught to how to do a 8-digit by 8-digit multiplication, but we can still do it. So that's the generalizability of humans. We don't necessarily have to see all the training data. We could apply existing rules to new tasks. Where we're trying to argue in the first paper is language model can't do that.
Thank you.
I'm curious about the baseline data transparency. You said that it indicates some issues at the data creation process. But I'm wondering, because the probability measure is produced by the language models, and at the start of the talk you were mentioning that language models don't have good estimations on the probabilistic of some common sense knowledge. So do you think it's trustworthy that the probability model produced on the answers?
Well, I think those are different problems. Essentially, language model can predict relatively reliable conditional probabilities, I think. But the thing I was trying to say in the first part of the talk is they can't model a joint probability of all these different separate concepts that is part of the common sense reasoning that we humans are doing. But when the input comes in as a sequential manner, I think the output predicted probability just represent how likely the model thinks is with this respect to this sequential, with the sequence. And with the current language model's ability, I think it's okay. It's apparently very trustworthy, like they're not producing incoherent sentences. So that's to address your second question. If the answer only baseline had some of the existing biases with existing biases in the data set itself, I think yes, that's true. Because one of the data set, the negative examples is incoherent, I remember. I can't remember which one, but the collection process of that data set is not trying to, I think the connection, the data collection process explicitly asks human annotators to write something unsensible. So that could explain why the answer only baselines performs very good without the existence of the question. But that's only one of the data set. The other data set, all the answers are coherent, and they should have equal probability under the model.
So was Colloquium not trained on the data set that you tested on?
I think we did a pretty careful data, trying to study the data contamination problems, and we did not train on the evaluation data. Okay, I'll go to the final section of the talk. So, as I said before, common sense answers are diverse and probabilistic. And I want to say especially in this kind of prototypical situations. Like, what do people usually do before they leave the house for work? And there can be several answers to this, like take a shower, brush teeth, drink coffee, eat breakfast, and all of this. And then each of the answers have different probabilities. When we're asking 100 humans to answer this question, there are 43 of them answered shower and 30 of them answered breakfast. So here we propose this data set called ProtoQA, where to measure this language model's performance on this, how good it is to map the human perception of this kind of prototypical question. So the questions in ProtoQA has multiple correct answers, and for each answer we have a score that is associated to the answer that represent how likely the answer is. And in this paper, we also propose a generative ranking-based evaluation. As I said before, we should not evaluate the models with a multi-choice problem, rather evaluate them generatively. So this is a generative ranking-based evaluation, where we evaluate multiple correct answers generated by model and reward models with the correct ranking of the answer list, and also reward model with a higher coverage of the answer list. And turns out there has been an American TV show that is doing this exactly same work called Family Feud. So we made use of this data set. This is actually how we get inspired. We just collected this data set from Family Feud, where for people who are not familiar with Family Feud is just asking this question, the host asks this question, and the competitors trying to guess which one has the higher probability. For example, here, name something that's easy to trip on when you get out of bed. Shoes, pads are more likely than rugs, but rugs are still very plausible. So yeah, we made use of this data set for training. The training part of this data set, we just scraped from the Family Feud fan website, and did some basic filtering to make sure the answers are not biased towards certain gender or certain culture. We ended up with around 9,000 questions, and this is how the training data looks like. One question, answers, and each answer has a number then associated with it. And the answer counts are aggregated by taking 100 answers from different people for the same question. For evaluation, however, we can't just take some of the existing data set because the models might have been trained on this data set. So we created new question by perturb the original questions, and then again ask for 100 human annotators. We did a manual clustering to cluster all these questions, all these answers into one specific cluster. For example, breakfast, eat breakfast, have breakfast, drink coffee can all referring to the similar thing. And then this is how we get our evaluation data. Where given a question, we have all the answers, but difference to the training data, we have all the surface forms of this cluster. So take a shower and shower, all these different expressions people might have been seeing, which makes our generative evaluation possible. So next I'm going to talk about the evaluation we proposed. And here, given this question, this is the ground truth, where for this ground truth answers, you have different surface form of the answer, and each cluster have a number. And this is the model prediction. We design
One quick question. Are you filtering the evaluation data the same way you did the training data for gender and cultural biases?
so we created the questions ourselves. When we create that data set, we make sure it's not too targeted to one group.
But what about the answers? Like the people that are providing the answers could be.
The answers, the crowd workers, we collect answers from our English speakers in the US. We did not ask for any more specific information about their background information. So we did not do more filtering on, like, from the answer distribution point of view. Even for the training data, we did a filtering based on the questions, not on the answers. Yeah. So yeah, the evaluation. We have the right-hand side, we have the ground truth, and the left-hand side is model predictions. We design a similarity-based matching algorithm to match this, just a similarity function. It's not an algorithm, it's just a similarity function to calculate the similarities between the predicted answer and all the answers in the cluster, and have used some Hunger matching algorithm to find the optimal matching between the answer and the clusters. So we essentially say all of that shower and eat get matched to this eat breakfast and have breakfast cluster. And then later, each of these answers will receive a corresponding score that is related to this cluster count. And then we have used this score, we designed two metrics to evaluate it. And basically, these two proposed metrics just captures both the more probable answers will get a higher score, and also a broader answer coverage. We make sure the answer also get a higher score. So this is the metric we were using, and let's look at the performance. This GPT-3 baseline is I ran last year, and in the paper we actually only had the fine-tuned GPT-2 baseline. From this, what we can see is in maximum answer at 1, which is basically hit at 1, the few shots GPT-3 is performing much more better than fine-tuned GPT-2. But when it comes to maximum answer at 10, meaning I'm looking at more of the more of the model predicted answers, the answer gets wrong. The answer gets wrong more, like the performance gap gets bigger, especially compared with human performance here. So after looking into this prediction myself, I'm trying to ask, why is the performance so bad? I reached to the conclusion of the model is having trouble predicting all these lower probability items. Essentially, it's the long tail problem. How can we make sure the model is predicting all these lower probability answers? And here, related to this, we have a recent submission that focused on this problem, where this purple part is the common sense. And the green part is uncommon common sense, is where we refer as the long tail part. And this paper just studied the uncommon common sense reasoning. The task is defined as this. We have a context, Cameron tried sushi for the first time and really disliked it. We have an unexpected outcome, Cameron will want to stay and eat more sushi. Why could this happen? So there could be happening, but despite liking the taste of sushi, Cameron decided to stay and eat more sushi plate to avoid disappointing his partner, who was excited about sharing. So this is the task we propose to study the model's uncommon explanation generalization ability, where we are asking for the model to generate explanations that makes the outcome more likely, and it has to naturally follow the context and also leave little information gaps in between. Go ahead.
I just want to understand you already. What do you mean by uncommon common sense? Do you just mean nonsense?
I hope you don't think this example as nonsense.
Yeah, I'm still trying to understand what you mean by uncommon common sense.
I guess the uncommon part comes from this uncommon outcome.
So you just deleted the common part.
the outcome is what the uncommon comes from. There is an unexpected outcome. And the common sense part is you could still use your common sense to explain the uncommon outcome, the unexpected outcome. Right? This part is common sense, and this part is uncommon outcome.
It has support. It has support in the distribution.
Yeah. That's a great way of putting it. It has support. Okay. Yeah, so in order to collect this data set, first we need uncommon outcomes. We just take the incorrect answers from social IQA and rock stories. And we also take human written uncommon outcomes with with the context. And in order to generate the explanation, we tried different ways. We have large language model generated explanation. We have human written explanation. And we have a collaborative version between human and large language models, where we ask the large language model to modify what human has written.
Why not the other way?
That's a great question, and I'll get to that later. Yeah. So the first question you might ask is, how's the quality of each of those generations? And this table shows the win rate preference judgments based on GPT-4, based on crowd workers on the left-hand side and GPT-4 on the right-hand side, of how do you prefer crowd, how often do you prefer crowd generations compared to large language models? So the base of this comparison is always GPT-4 generations. And as we can see here, the crowd generation are actually not that favorable compared to large language model predicted, the generations. It wins only 20% of the time and lose 53% of the time. But however, the combination of crowd workers and large language models has a much higher winning rate and an equally good rate. So later we went to details about the qualities of these explanations from different models. First thing we did is the outcome likelihood. If your outcome becomes more unlikely, how does the explanation, the quality of the explanation change? On the likelihood equals 3, which is the green bar, is the most likely outcome. And then the likelihood equals 1 is the most unlikely ones. This is the win rate with human plus LLM versus large language models. So as we can see, as the outcome becomes more unlikely, human plus large language model explanations are preferred more compared to large language model explanations. And this is just one dimension of the analysis. We did more analysis on the length of the generation, the explanations from different annotators. And one problem we see with human-generated explanation is they are generally much more shorter and compared to the large language models. But after elaborating the human generations with large language models, the lengths get much more longer. And then, so that's just the length, but how much information is actually contained in this generation? So we calculate the entropy of an n-gram distribution in this uncommon social IQA aspect, where the entropy, we use entropy as a measure for lexical diversity. Where we see here, this crowd plus language models gives us the most diversity, meaning the original content of the crowd workers is good, but humans do not like to elaborate on what they say, especially when crowd workers are rushing to get to the next task, they tend to give very short explanations. But after using large language models to elaborate, it becomes much more informative. Well, we did a similar experiment, we did a similar kind of generation with large language model modify its own generation. It's the LLM square. That do not have much more information compared to like the modify the human ones. So this is the data set analysis, and in the paper we also proposed an imitation learning framework for smaller models. But I won't go into details about this part, and I will just go say some key takeaways from this uncommon sense aspect. The generating explanations using GPT-4 for uncommon situations works fairly well, but human generations are more creative and contains more information, thus the combination of both works the best. And the performance drops as event becomes more unlikely. And the final question is, how can we evaluate this explanation? That's wrong. How to evaluate explanation? That's wrong. How to evaluate explanation is what I meant. Because in the paper we mostly use GPT-4, and I would try to avoid one of the findings we use with GPT-4 is the model tends to take a stand on like which one is better, is less likely to produce equally good or equally bad kind of option, where in a lot of the cases the explanations are equally good. So that's just some open questions from this part. Any questions? So that's concluded my talk. This is a much longer talk than I expected, but I thought we had very good discussions. So thank you, everyone.
And so everyone,